All right, so let's look at this problem here. This is asking us to draw the stereoisomers for these following amino acids. So we have leucine, we have isoleucine, okay? So I drew leucine here on the left, and we have CH3, CH with a methyl attached. We have CH2, and then we have this CH here, which is attached to a carboxyl and an amino group here, right? I'm going to redraw this so you can see every bond clearly, okay? Now, I do notice a stereocenter here. Why is this a stereocenter? Well, it's attached to a hydrogen, it's attached to a CH2, and it's attached to two very different things here. So it's attached to four different things, making it a stereocenter, okay? I'm going to put this sort of into like a hybrid Fisher projection here, just so we can rule out if this is a diastereomer or not, okay? So this is the same compound. I just wrote it a little differently. We have our stereocenter attached to an amino, a hydrogen, a carboxyl. This is our CH2, which is attached to a CH and two methyl groups, okay? This is not a stereocenter because it's attached to two hydrogens. Rules it out. This is not a stereocenter because it's attached to a methyl group, okay? If this was something else, I don't know, nitrogen or something, this would become a stereocenter. But right now, it's not, which makes this easy, okay? So, how can we draw a stereoisomer of this for leucine? Well, let's start by copying the exact compound. And we can make a mirror image of this. Let's make a nice, clear separation here. Okay. All right, so in order to do that, we need to assign some stereochemistry to this first. Now, the easiest thing to do is to keep this and this in plane. If you have a carbon group, you usually want to keep those in plane, especially when you're working with a Fisher projection, okay? So we just need to assign some stereochemistry to our H and our NH3. Let's make it easy for ourselves, and let's put our hydrogen on a dashed wedge. And let's put our amine here on a solid wedge. Okay, so let's see. So we're hitting a nitrogen immediately. This is going to be our one group. We're hitting a carbon. This hydrogen is going to be our four group. We're hitting a carbon attached to an oxygen. That's going to be two. And we're hitting a carbon attached to two hydrogens and another carbon. This is going to be three. Pretty sure that's correct. You go to your immediate things first. All right, nitrogen is going to be heavier than carbon. These oxygens look tempting to rate this as a number one, but you're looking at the first thing first. You hit a carbon, you hit a nitrogen. Nitrogen's going to be heavier. Okay, so this is 1, 2, 3. We're going to the left. Fourth priority is in a dash wedge, which is where we want it to be. Hence, this is going to be, well, here's the thing. I did kind of draw this in a Fisher projection. I sort of drew it in a Fisher projection. I sort of didn't. If that would be the case, 1, 2, 3, this would be S. This would stick with S. However, in a Fisher projection, technically this is going out. This is going out, and these are both solid. So let's stick with a Fisher projection. I know this sucks and this is annoying. You know, this is kind of like a hybrid Fisher projection. I'm just going to stick with this. I'm going to say this is a perspective just turned sideways. And I'm going to say that this is S. 1, 2, 3, going to the left. I'm going to say that that's S. All right, we're going to make this R. Okay. The only thing we need to do to make this a mirror image is swap this, and that's, and I'm going to put this as a wedge. I'm going to put that as a wedge. And I'm going to put this as a hydrogen. Okay, so if we're looking at this, if there's an invisible mirror here, everybody has a partner. Everybody is an exact mirror image of what's across from it. This here is an exact mirror image. And it's important that these are wedges facing at each other. If this was this, I believe that would be an identical compound. You don't want that. And if you build the model for this, you would figure out how. So let's figure out that if this is R, we've made mirror images. Okay. Carboxyl will stay 2, our NH3 would be 1. Hydrogen would be 4, and this one down here would be 3. If we do 1, 2, 3, we're going to the right. This is where we want it. This would be R. So we have gone ahead and made 2 mirror images of each other. Okay. Just for the sake of this, let's try this. Let me show you something. Let's use Fisher projection rules. Okay, and let's say in Fisher projection, you can always think of like the guts of a fish. I know or you can think of a crazy bow tie that looks like this. Okay, so let's use those rules for a second. Let's erase this. See, the reason I don't like to do that swap. Whatever, let's stick with it and see if it works. And we're going to say this is dashed and this is dashed. Okay, we'll stick with our priorities. I don't know why I erased that. This was 3, this was 2. 1, 2, 3, this is left. However, this is now an R isomer and Fisher. Okay, let's do the same over here. Bada bing, bada boom. Our stereochemistry in there. This is 2, this is 1, this is 3. The reason, I'm sorry, that I reversed this was if I'm doing 1, 2, 3 to the left, our fourth priority is not in a dashed wedge, so we need to reverse, which is why this is R. All right, if we're looking at this, now we're doing 1, 2, 3, R. However, this is not where we want it, so this would be S. So there's 2 different ways to confirm that these are mirror images. Okay. Now let's look at, we're going to stick with strict Fisher projection for isoleucine. Let me put this on another page. Because what happens with isoleucine is we have 2 stereocenters. Let's confirm that we have two stereocenters. Carbon is attached to a hydrogen, a carboxyl, an amino, and a carbon that's attached to not oxygens. You know, it's carbon versus carbon, but this is attached to a methyl and a hydrogen. That's why this is a stereocenter. This carbon is attached to a hydrogen, an ethyl, a methyl, and a carbon that's attached to all this stuff. So that's why that is a stereocenter also. Okay, let's assign some priorities here. Hydrogen here will be 4, amino will be 1, carboxyl will be 2, and this carbon will be 3. Let's say that this is our orange stereocenter. For this one down here, we're going to give hydrogen 4. We're going to give it let's carbon attached to 3 methyls is usually your 3. This is a carbon attached to a heavy nitrogen, so this is definitely going to be 1. And this is a carbon attached to 2 hydrogens. Let's spell that out just so it's a little easier. And attached to a carbon, so this is going to get our second position. That's going to get our second position. Let's double checking this. Yeah, that looks good. Okay, so I'm not going to draw, but just remember that for Fisher, when you're assigning stereochemistry, it's going to look like this. Okay, so if we're going up top here and using our orange numbers for this, it's going to be 1, 2, 3. We're going to the left, which is going to be S. However, our hydrogen is not in a vertical position. So 1, 2, 3. So this will be R. And this one down here is going to be 1, 2, 3. Left, again, not where we want it. So this is going to be R also. Okay. All right. Now there should be 3 stereoisomers, 3 isomers that we can make for this. Okay. It's for a total of 4. All right. First up is let's select this whole thing, and we're going to make the mirror image. That's the easiest thing to do for something like this. Okay, so to make the mirror image, what do we do? Let's get rid of the R. Let's get rid of the R. Okay, to make a mirror image, all you need to do is look for an imaginary plane and make sure that everybody has a buddy. Okay, all you need to do, this is fine, but we need NH3 to have its buddy here. We need methyl to have its buddy here. So all we're going to do is swap these. And we're going to put NH3 here and the corresponding hydrogen here. Now, before I continue, what I just made here is a diastereomer. That's 1. That's a diastereomer. Because all you do is make one change. Because I made a change, this should be now S. This is still R. I made no changes there. This should be S. Let's confirm that this is S. Well, this is 1. This hydrogen is still 4. If I connect my dots and do 1, 2, 3, this is R. However, hydrogen is still not in a dashed wedge. So this is S. So I just made a diastereomer of this. Okay. The other way that I can do a diastereomer of this is if I kept this NH3 here, and I kept the hydrogen here, just like this, but I swapped my methyl with my hydrogen here. If I brought this methyl here, and this hydrogen here, I would then make this S, and that would be the second diastereomer, okay? But what I'm going to do, because I want to make an enantiomer, is complete my transformation of a mirror image, putting this here, putting this here. So now everybody's got a buddy. NH3 is staring at itself in the mirror. Methyl is staring at itself in the mirror. Okay? And this is erythro. Well, why is it erythro? Because our hydrogens are on the same side. 3O, because the highway 309 has 2 lanes. 3O would have hydrogens on opposite sides. That would be the 3O, a 3O isomer, okay? However, what I just made here is not a diastereomer. What I made here is an enantiomer because it's a mirror image, okay? For the sake of completion, I'm going to show you all 4 stereoisomers on the same page. Let's put the diastereomers under here. We're just going to swap one thing to 1, 4. H3 plus, and this was 1, this was 4, this is 1, 2, 3, going to the left, that's going to be R, because still hydrogen is not where we want it to be, which is completely fine. Carbon, we didn't make any changes to 1, 2, 3, going to the left, so that is also going to be R. This is R. So we have RR, we have SR, we have RR. Hold on. Oh, hold on. This is the enantiomer. I'm sorry. This is not R anymore because I completed my switch. This is going to be S. Let's double check. 1, 2, 3 going to the left. 1, 2, 3 going to the left, which should be S. No, that should be R. 1, 2, 3 going to the left, which should be S. Hydrogen's not where we want it. That should be R. 1, 2, 3. Oh, forgot to change my values here. Hydrogen is 4, methyl is 3. Sorry about that. 1, 2, 3, going to the right. Hydrogen's not where we want it, so this would be S. So an enantiomer is always going to be R and its opposite S. In this case, R, and this opposite S. I know, sorry, this can be very confusing. I did the same thing down here. 4, 3. So this is going to be 1, 2, 3, going to the right. So I'm going to reverse it. This would be S. So we have an RS. And last but not least, the other easy thing you could just do is once you have one diastereomer, you're just going to draw its mirror image. So in order to do that, we're going to say NH3 plus H, H, and CH3. This is 1, this is 4, this is 3, this is 4. 1, 2, 3, going to the right, this is now S. 1, 2, 3, going to the left, that is R. Okay, so we have S, R. I'm going from top to bottom. R, S. This up here is S, S, and this up here is R, R. So those are 4 stereoisomers. These are enantiomers. These are enantiomers. Okay. If we're looking at this, it has 2 diastereomers. If we're looking at this, it has 2 diastereomers. If we're looking at this, it has 2 diastereomers. Okay? These are not mirror images. These are not mirror images. Okay? You only have one mirror image, which is why these are mirror images, which is why these are mirror images.